10 years ago, scientists heard the universe for the very first time, not through light but through ripples in space-time itself, gravitational waves. Now in 2025, the LIGO, Virgo, and CAGRA teams have just announced some of their clearest and most astonishing discoveries yet. From black holes heavier than we thought possible to the laws of thermodynamics written on the fabric of a black hole, this is the story of how gravitational waves are rewriting our understanding of the cosmos. Hey everyone, I'm Naeem. Today we're diving deep into how gravitational wave astronomy has transformed astrophysics in just one decade, and what the newest 2025 discoveries tell us about black holes, neutron stars, and the very laws of physics. In 1916, Einstein predicted that massive objects, like black holes and neutron stars, stretch and squeeze spacetime as they move. When two orbit each other, they send out ripples, gravitational waves. Detecting them is insanely hard. LIGO's twin detectors in the US, Virgo in Italy, and CAGRA in Japan use 2-mile-long laser arms to measure distortions smaller than a proton's width. Yet those tiny wiggles encode huge amounts of data. The masses of colliding objects, their spins, even their distance from Earth. Yet those tiny wiggles encode huge amounts of data, the masses of colliding objects, their spins, even their distance from Earth. September 2015. Two black holes merged 1.3 billion light-years away, and humanity detected gravitational waves for the first time. It was the ultimate confirmation of Einstein. Then, August 2017, a neutron-star collision. For the first time, astronomers saw light and gravitational waves from the same event. That proved these collisions forge heavy elements like gold and platinum, literally showing us where cosmic jewelry is made. Fast forward to 2025. After upgrades, the collaboration released data covering 128 new binary mergers between mid-2023 and early 2024. That's more than double the previous count. Among them, a neutron star-black hole merger, where a relatively light black hole, 2.5 to 4.5 solar masses, swallowed a 1.4 solar mass neutron star. Scientists hope to catch electromagnetic light from the neutron star being shredded, but no luck this time. Still, spotting such systems confirms they exist. The most massive binary black hole merger ever detected, more than 200 solar masses combined. One black hole is so heavy, scientists didn't think such giants could form from a single star's collapse, and in July 2025, the clearest gravitational wave signal ever, a near clone of the very first 2015 event, but now LIGO's detectors are so sensitive the signal stood out 3 times more strongly against the noise. And in July 2025, the clearest gravitational wave signal ever, a near clone of the very first 2015 event, but now LIGO's detectors are so sensitive the signal stood out 3 times more strongly against the noise. And in July 2025, the clearest gravitational wave signal ever, a near clone of the very first 2015 event, but now LIGO's detectors are so sensitive the signal stood out 3 times more strongly against the noise. With that ultra-clear signal, scientists confirmed that the final black hole radiated exactly as general relativity predicts. They also tested something profound: the laws of black hole thermodynamics. The surface area of the final black hole was larger than the 2 originals combined, meaning entropy increased, just as Hawking and Bekenstein predicted decades ago. In other words, gravitational waves aren't just proving Einstein right. They're showing us that black holes follow their own thermodynamic rules, a bridge between gravity, quantum mechanics, and the arrow of time.